This quick video today is meant to help you to determine how many significant figures are in a number and what you do with significant figures. So the first thing we need to do is we need to define significant figures. So significant figures are, as I've written here, all digits you know with certainty plus one uncertain digit. When we're working with significant figures, we want to assume that we're always performing measurements. Significant figures do not apply to exact numbers or infinite numbers. So for example, 1 dozen eggs is 12 eggs. There are an infinite number of significant figures or a non-tangible number of significant figures because 1 dozen is 12. We can't define it any other way. But if we are taking a measurement, say we wanted to talk about something that was 12 grams, we would know that the 12 grams was estimated at least to a certain extent. So that's where it kind of all starts. With significant figures, you're assuming that a measurement is taking place, and when you are performing that measurement, there is an aspect of it that you're not completely certain about. So when we perform measurements, we always are going to measure with everything we know with certainty plus one uncertain digit. So if you picture having a container that's got tick marks on it, say a thermometer, and if you know that the tick marks in the thermometer each represent 1 degree Celsius, that means that you can be certain to that measurement to the 1 degree Celsius, which means you are uncertain to the next digit, which would be the 10th of a degree Celsius. So if you'll just pardon this terrible drawing I'm going to do here, if we were to draw a picture of what's going on here? Here we go. If we're going to draw a picture of a container, and we're going to mark a line here, that's a terrible line. We're going to mark a line here, we'll call that 1, and we're going to mark a line here, and we'll call that 2. And now let's say we've got something in the container that fills it to this level right there. Okay. When we make that measurement, what we know with certainty is that the container is between 1 and 2, so it's going to be 1 point something, all right? And we're going to estimate how far it is in between. So you might call that 1.5, whatever that container is. You might also call it 1.4, which would be an acceptable number. You could even call it 1.9, which is an acceptable number by the rules. You can clearly see that this is not skewed to be all the way up to 0.9, but you could call it that. These are all acceptable. What you cannot call it is 1.75. And the reason why that doesn't work is because your 10th place is your estimated place. You know it's 1, you know it's not 2, so it's 1 point something. So you have to stop at the 10th place. That's why 1.5, 1.4, 1.9 are all acceptable numbers. 1.75 would not be. Neither would 1.66. And the reason why is your 6, the first 6 in the 10th place is your estimated digit, which means your 100th place 6 is estimated as well. You can only have one uncertain digit. Okay? So now if we get rid of all this stuff right here, let's see if I can figure out how to do that quickly. No, I don't want to get rid of that. Get rid of all this stuff right here. And then come over here. Get rid of these items right here as well. Not that. And get rid of that one right there. We're all set. Now, when we're looking at a number here, we want to try to figure out when we look at that number how many significant digits are in it. So we're going to take a look, and for example, we're going to have a number that is listed as 4.003. Now you might be looking at my picture here thinking, what on earth is this geography lesson that I'm going to be teaching you? Well, there's a really simple set of rules that I want to apply in order to figure out the number of significant figures. We're going to refer to what's called the Atlantic rule or the Pacific rule. We're going to utilize the Atlantic rule when you have a decimal point absent. We're going to use the Pacific rule when you have a decimal point present. Okay, this is all based on the decimal point. Now what we're going to do is we're going to take a look at the number that we have, and we're going to first identify is the decimal point absent or is it present. In this case, 4.003 has a decimal point present. The way that the rule works is you start counting your digits with your first non-zero on the Pacific side of the number because we have a decimal point present. So the first non-zero is a 4. We're going to count 1, 2, 3. this digit right here, this measurement right here, we should say, actually has 4 significant figures. Okay, so now we can take a look at, whoops, try to do that again. Let's go back this way. And we want to go forward to there. Sorry, been a little while since I used this program. Trying to get back in the swing of it. No, we don't want to do that. Oh my goodness, this is a mess. Here, let's do this. Oh my God, this is terrible. My precision is not really good. Hey, see what I did there? Anyways, all right, now let's move on. Let's take a look at another digit. Let's say we've got, I'm not going to even write it up there this time. Let's say we've got 0.0025, 0.0025. So picture plopping that number directly on the Midwest of the United States. We can see that the decimal point is present again. Start with the first non-zero on the Pacific side, which is the 2. We can start counting here, 1, 2, 2 significant figures. How about 0.002500? So it might look like that's the same value, except that when we start with our first non-zero on the Pacific side, which is the 2, we count 1, 2, 3, 4, 4 significant figures. So what's the difference? In this number, that 5 is your estimated digit, and this number, the 0, is your estimated digit, which means you have a much more precise instrument. How about a number like 500? Well, in this case, we have a decimal point absent. So if the decimal point is absent, we're going to apply the same rule, except we're going to start counting our first non-zero on the Atlantic side. Atlantic side of the number, we start here. Oh, we can see the first number is a 5, so we start counting here, and there's nothing else. There's only 1 significant digit in that value. And then finally, we could look at 500.000. Decimal point present again this time, so start with the first non-zero on the Pacific side. Okay, over here, 1, 2, 3, 4, 5, 6. We can see that there are 6 significant digits in this value. Okay, and this can apply to any number of circumstances. It applies to any number. Now, when we're working on this, we also want to consider what do we do with significant figures. Well, when we're adding and subtracting numbers, we need to minimize the uncertainty by rounding the digit with the fewest decimal places. So the first thing you need to do is you need to do your typical operational math. So you have 1.23 and say plus 1.4. And when we add those two up, you end up with 2.63 as your, as your raw value. Now, we want to round our final answer to the fewest decimal places. So we can see that we have only 1 decimal place here. We have 2 decimal places here. So we're actually going to round to the 1 decimal place. So that 2.63 will actually round to be 2.6. And the reason why is that 4 is uncertain in the hundredths place, all right? And the 3 is uncertain in the, the 4 is uncertain in the tenths place, the 3 is uncertain in the hundredths place on the 1.23. You can't have 2 uncertain digits. So you go to the first uncertain digit, okay? Let's take a look at another number. Let's take 6.38, and we'll subtract from that 1.2. And when we perform that operation, you end up with 5.18. I don't know why I wrote a 5, 5.18. And then we can try to figure out the place we're going to round to. Okay, so we look at 6.38 uncertain in the hundredths, 1.2 uncertain in the tenths. You can only be uncertain in the tenths, so we're going to round to that place right there. 5.18, we're going to round off to be 5.2. Okay, and then finally, one more example. We could look at 8.965 minus 3 decimal equals, okay, that's going to be 5.965. We can see that the estimated digit here on the 3 decimal is the ones place. The estimated digit here is the thousandths place, which means you can only round to the ones place, that spot right there. This is going to round off to 6 decimal. Now, that's a ridiculous measurement because you've got something that's precise to the thousandths place, something precise to the ones place, and you probably would never do an operation like that. But just for the purposes of conversation, that's how it would work. Okay? When you're multiplying and dividing numbers, same concept. We want to minimize uncertainty but instead we're going to round to the same number of places as the fewest significant digit. So I'm going to pick some really easy numbers here. Let's say we've got 2.000, and we'll multiply that by 3.0. Okay? If we were doing our typical math, we would find out that that works out to be 6.0000. Okay? However, we want to look at our significant digits, and we want to realize that we are going to round to the fewest number of significant digits. So we're going to apply our rules. Pacific rule, decimal point present, 1, 2, 3, 4 significant figures here. Pacific rule, 1, 2 significant figures right here. You want your final answer to be rounded to the fewest number of significant figures. 4 significant figures in the first, 2 in the second. Your final answer should be rounded to 2, so we would round that to 6.0. Okay, let's take a look at another example. Pick something a little bit different. Let's take 3.125, and we'll multiply that by 2.6. Okay, now I can't do that off the top of my head, so I got my calculator out here. And so we have 3.125 times 2.6, and I get 8.125. So now we want to identify the number of significant figures in each number. This one right here is going to be 4, Pacific rule, decimal point present, 1, 2, 3, 4. This one here, decimal point present, 1, 2, so that gives us 2, coincidental. And so we're going to round our answer to 2 significant digits. This is going to be rounded to 8.1. Okay, try one or two more. So let's take 3.1723, and we'll multiply that by, I don't know, 294, whatever that ridiculousness is. Okay, so again, 3.1723 times 294. The raw answer that we get, and this is a raw answer, 932.6562. Okay, so that's just ridiculous when we do it. Please do not write all the digits in your calculator down. We look at this number up here. Decimal point present, 1, 2, 3, 4, 5 significant digits. This one here, decimal point absent. We start on this side, 1, 2, 3 significant digits right there, which means your final answer has to have 3 significant digits. We look at this 932.6562. We are going to round it to 3 significant digits, so that's this right here. The 6 is going to take that 2 and round it up, and what we end up with is 933. Okay, so that's pretty much the deal. That's how this works out. Hopefully this was helpful to you. Hopefully you'll be able to apply significant figures easily, and if you have any questions, leave it in the comments or send me an email and let me know what you think. Thanks.